But unlike the Caledonian Star, the Bremen also lost her engines. The ship and all on board were now in desperate trouble. Unable to power her way through the sea, the ship drifted side-on to the waves, exposing her weakest parts.
When the engine failed, the ship lay transversely to the sea, and the sea rolled crossways to the ship against the big windows of the restaurant.
This was the worst situation possible. The restaurant windows are extremely weak. If they were hit by any large wave, water would flood in and the ship would sink.
We would have capsized. It would have broken through or smashed the windows.
It was now a race against time. To turn the ship away from the waves, they desperately needed to restart the engine. But the starter generator was in pieces on the floor. If they couldn't start the engine, the ship and everyone on her was doomed.
We came from the Antarctic and had nearly 0-degree water temperature, and the air temperature was the same. In those high sea conditions, it wouldn't have been possible to put lifeboats or life jackets or life rafts in the water. As well as that, the passengers we sail with aren't the youngest anymore. I doubt any of us would have survived.
So, in dark, rolling seas, they set to repairing the engine. All the time, the waves were smashing against the windows. And then they got lucky. The engine finally started.
Then for the first time, I had hope we would make it. They are wonderful moments when you know everything works normally again.
Both the Caledonian Star and the Bremen were fortunate to survive. But their experiences challenged everything known about freak waves. There are no currents or local conditions to cause rogue waves in the South Atlantic. According to traditional theory, such waves should be incredibly rare. Yet here were two, within days of each other. So what was going on? Science mobilized every technology to solve the mystery. Using a new radar satellite, Susanne Lehner of the German Aerospace Center began searching for freak waves around the globe.
Now, with these radar images, you can really see the individual waves. You can see wave lengths, wave directions, wave grouping.
The European Remote Sensing Satellite travels across the ocean using highly sensitive radar to get a detailed picture of the sea surface. It can pick out individual rogue waves from anywhere in the world.
What we get is an image like this one. This is actually the radar image with the highest wave we found on all of our 30,000 images we analyzed. This is a 30-meter wave here, the high crest followed by a very low trough.
This is exactly the size of wave which hit the Bremen and the Caledonian Star. The sort of wave that science said was practically impossible. And in just 3 weeks' worth of data, they found over 10 such huge waves out in the deep ocean.
What you can see here is this highest wave we found of about 30 meters, that is color-coded in red. The next highest waves here are about 27-meter high waves, color-coded in orange. We find another high wave here in the North Pacific. This is again a kind of 26-meter high wave here. We did not expect to find in this limited amount of time so many of these extreme wave events.
If the satellite data is right, it looks as if freak waves occur in the deep ocean far more frequently than the traditional linear model would predict. The question is, why? The answer seems to lie in a completely different branch of science. Al Osborn inhabits a strange mathematical world where almost anything can happen. It's the bizarre non-linear world of quantum physics. In this world, objects appear and disappear according to one remarkable equation, the Schrödinger equation.
The Schrödinger equation, quantum mechanics. We have TV programs called Quantum Leap and so on and so forth, so we all think we know something about that equation. There's a version, however, modified, that describes deep water waves.
Osborn is one of the world's leading wave mathematicians. For 30 years, he's been obsessed with the theoretical waves described by the Schrödinger equation. The equation describes a theoretical water surface where huge waves can suddenly leap up out of nowhere, where for some reason normal waves become unstable and grow huge.
The physics of the nonlinear Schrödinger equation we can see in this simple example. In the beginning, it doesn't seem like there's anything happening, and we could all just give up and go drink a beer if we wanted. On the other hand, we could keep moving forward and maybe something will happen. What we'll see is this central wave here is going to start to grow. It's growing because it's robbing energy from its two nearest neighbors. So here it's starting to come up. You see it's growing. It's stealing energy from the nearest neighbors. And these waves are starting to drop. See how this is coming down here? Look at that decrease. And now, in its full glory, it's a very large wave. It has two smaller waves on each side and two rather deep holes in the sea around the peak.
In Osborn's theoretical world, these non-linear waves could grow into monsters. But the idea of waves becoming unstable like this in the real world was so outlandish that oceanographers said it could never happen.
If you talk to people who know something about ocean waves, nobody was going to take this theory seriously.
Until someone sent him the profile of a wave. It was the one that hit the Draupner oil rig in 1995. The New Year wave.
For me, it changed everything. Really changed everything.
The New Year wave looked identical to one of his theoretical non-linear waves.
I was flabbergasted. Absolutely flabbergasted. It just looked exactly like one of these exotic solutions to the nonlinear Schrödinger equation. One of the ones that we threw away over the last 30 years because we said, this kind of thing can't happen. This kind of thing is just too strange. Yet, it just sits there and it looks at you, and you have to entertain the possibility that it is a real effect. And it might really have something to do with these extreme waves in the ocean.